Hey, everybody. Welcome to the March SJAA Imaging SIG meeting. Tonight we have Daniel Parrott, who's going to talk to us about the Tycho Tracker, his work tracking asteroids and how amateurs can help do that very same thing. Daniel, take it away.
Thank you. So let me go ahead and start off. I will share my screen here. So this is what I've entitled Asteroid Hunting and Photometry with Tycho. So Tycho is the kind of the software that I've been working on these past couple of years. And so what I'm going to start off with is basically detection of asteroids. So before you can do anything interesting, you have to first be able to detect the object of interest. So I'll talk into some detail about how you would go about the detection process. And then I will follow that up with once you've detected it, then what kind of measurements can you perform? So this would involve primarily two different subjects here. We can consider astrometry, which is concerned with the precise positioning, location of the object, so where it is at a given point in time, and then photometry, which is concerned with how bright the object is over time. So you can consider a light curve of an asteroid, and from that you could deduce its rotation period and glean other characteristics of the object. So we first want to be able to detect the object, and then we can do measurements. And this also leads into other fields as well. With photometry, you could do measurements with variable stars, exoplanets, and a more recent one I could talk a little bit about is the James Webb Space Telescope. So I have some data on that that's kind of interesting to look at. So it's a moving object, just like an asteroid, if you wanted to say it pertains to this discussion. So again, detection would be the first part. And I'm going to talk just a little bit about how it's done today. So this is what I consider to be the quote unquote conventional technique. So this is commonly used by the professional surveys. They have these large 1 meter class instruments typically. And this involves taking 3 or 4 images, typically spaced 20 minutes apart. So you'll take an image, a snapshot of some field of view of the sky, and then 20 minutes later, you'll follow it up with another image and so forth until you have 3 or 4 of those exposures. Now, this is great. You get a lot of sky coverage. However, one of the downsides here is that the signal to noise ratio is limited to that of a single exposure. So a lot of you are familiar, I'm sure, with the principle of stacking. So that's kind of what we're able to do now with a technique that is called synthetic tracking. Others might call it also digital tracking, but the common term here that I'm going to be using is synthetic tracking. And so with this technique, you're actually able to detect objects about 10 times fainter than would be possible with the conventional technique. So this relies upon having typically dozens or more exposures. And what you wind up doing here is you will continuously dwell on a field. So you'll take this field of view and just take one image after another. There won't be any gaps between them. Again, this is a technique that's become more popular, especially with the advancements in modern hardware. And I'll go into a little bit of discussion on that in just a moment. But it's also useful not just for discovery, but also recovery. And what I mean by recovery is that whenever you have just initially discovered or detected an object, you have very high uncertainty in its motion, typically. So you've just got a few measurements, a few observations from one night, and you want to try to follow it up the next night. Well, sometimes you can and sometimes you can't, just depending upon the uncertainty of those measurements. And so Catalina Sky Survey, just as one example, they've been using the Tycho software. In 2021, they used it to recover 15 of their near-Earth objects that would otherwise have been lost. And so synthetic tracking is proving useful for both of those use cases. And so again, it's able to detect objects having a wide range of motion. And this is because it's not limited to just one motion vector. It can explore thousands of different vectors. And so here's an example on this slide here. These are all what I call trial stacks of the same object. So what I mean by that is an object can have a speed and it can also have a position angle. So this defines its motion. And what you're trying to do here is create a trial stack. You're trying to stack those images according to its motion. And so just a way to visualize that is at the very center here, you have what would be considered the ideal trial stack. And so then away from that, you have other stacks that had not quite the correct motion. The speed might have been too fast or too slow, or its position angle was off. So what you're able to do, again, with modern hardware is basically in a brute force fashion, you can explore these thousands of different motion vectors and then extract the object that had this correct motion here. So again, these advancements that have taken place, I'll talk about 3 of them here. So we've had certainly a lot of improvements with graphics processing hardware. So GPU hardware has come a long way. Then we've also had the advent of full frame CMOS cameras. And this is important because with this technique, when you're taking these short exposures, you want to have low readout noise. And so these CMOS cameras are well known. They have a low readout noise. And then finally, we also have now the availability of large aperture telescopes with a fast focal ratio. So the Roe-Ackermann-Schmidt astrograph telescope is one example. And of course, a lot of folks are probably also familiar with Hyperstar. So these both operate typically around f2. So just giving some numbers here. In the year 2020, just first starting out with Tycho, we had 5 near-Earth objects discovered with it. And then in the next year, in 2021, 68 near-Earth objects were discovered, as well as 2 comets. And these are all from amateur astronomers. So I'll just point out one example here. This is one discovery, 2020 BU6 that had a size of 860 meters. And this is one of the largest near-Earth objects found by an amateur in recent years. And so here's a diagram showing what its orbit looks like. So you can see here, went past the orbit of Mars, but it is considered a near-Earth object here. And so this is what it looks like on raw image data. So here is a single exposure, 130 seconds in duration. And this is a zoom 2x. And just a single exposure, you can't really see the object. It just looks like it's mixed in with the background noise. So it's, again, on a single exposure, you can't really do much with that. But here we have a stack of 21 exposures. And you can start to see this object presents itself with this stack of 21 exposures. And what I'm going to do here is just show, as I zoom out, you can kind of get an appreciation for this field of view. So here's 1x zoom, and then I zoom out more, and then a 1/4 zoom. And then so this is really brings into focus what's really nice about these full frame CMOS cameras. You have this nice wide field of view. You can cover a lot of sky with them. And so it's pretty cool that we're actually able as amateur astronomers to have this kind of data at our fingertips. So I'd like to just, before I go on to any example data here, did anyone have any quick questions? And if not, then I can just, I'll proceed further. Okay.
Yes, I have one question for you. When you're doing this synthetic tracking thing, you must already be taking a educated guess as to what rate you should be tracking the scope in order to get an image of the object that you're trying to shoot. Is that correct? Are you doing an iterative attempt by finding what you think it's doing in order to catch the object?
Right. With the synthetic tracking, you're actually just you're doing sidereal tracking. You're tracking the stars, and then you do the actual tracking of the object after the fact.
Okay, so you're hoping you can find it on a regular star field, and then once you do, you try to figure out how fast it's moving and just track on the, use that speed to guide on the field to help. And that will improve the magnitude reach for that particular object then.
Right. So whatever you do synthetic tracking, you can do what's called a kind of a blind search. So you're going to explore a wide range of speed and position angle, and this
right.
is okay.
Yeah, that was what I wanted to know. Yes.
Okay. Yeah, I will
Thank you.
show some examples of that with this data.
Can I ask, so you take a patch of sky, like it looked like around a degree or two, in width, and you take a shot and say, is there an asteroid in my field of view? It sounds like, and shoot it for 20 minutes or half an hour. What are the odds that there's something in there?
The odds are pretty good, especially if you are imaging at the ecliptic. And so, yeah, I actually, using just a 127 millimeter refractor, I was able to, this was just kind of one of those, see what would happen kind of things, but I imaged at the ecliptic, and even with the smaller instrument, I was able to detect over 200 asteroids in the field of view.
Okay, thanks.
Yeah. Okay, so I will go ahead and move forward with some of these examples. The first example here will be what I call the data set that's available with the Tycho user guide. So if you ever have an interest in trying out the software, it comes with some example data sets, and this is one that kind of gets you started. And then I have another one here, asteroid 1884. That 1884 is its number. So a lot of minor planets will be numbered, and it's also known by the name Skip. And then finally, I thought it would be interesting to take a look at the James Webb Space Telescope. So I took a series of images of James Webb as it was en route to the L2 Lagrange point. So I'll be showing off some of that data. So I'm going to go ahead and start off with the Tycho program. So hopefully everyone can see that here. So this is what Tycho looks like. And when you launch it, it's just kind of a bare bones just presentation. You start off with the image manager. So that's what this is here. And this is basically a list of whatever images you want to work with. So I'm going to go ahead and add some images to my image manager. And this will be, again, I'm starting off with the data set for Tycho user guide. And so I've selected my images and I brought them into Tycho. It tells me I have 60 images here. Each one is 2 minutes or 120 seconds in duration. And the total exposure time is 2 hours. So 60 of them, you get the idea. So I've also already plate solved these images. So we have a plate solution. And just if I want to, I can go ahead and do view images. So from the main menu here, you can go to Action, View Images. And this brings up what I call the image viewer. So what we're looking at here, these are just basically the raw images here. And they've been calibrated, but basically, you can zoom in, you can pan, do whatever you want to. So this is just getting started. Now, we might want to know, okay, a question earlier, would we have any asteroids in this field of view? So one way I can answer that question is I can go to File, Load Known Objects, and that's going to bring up this known object module. And so what this does for us is it tells us what are the known asteroids, comets in this field of view. So here is a list of all the known objects in this field of view. And if I want to, I can click on one, and it's going to center that object. So I've clicked on 38826, that's the number of the asteroid, and I can zoom in. Now, I'll notice that I need to update my observatory. So I took these images with an observatory located in Australia. So Q62 is Sighting Spring Observatory. So I'm just going to make that my active observatory. The reason that's important for this example is that if you want to have the precise positioning, the top eccentric coordinates to be precise, Then it has to know sort of the lat long, basically the location where you took those images. So I've updated that. I'll just refresh this here real quick. And now you'll notice that whenever I click on 38826, it is now centered correctly in the crosshairs. So this is the asteroid here. Again, that's on a single exposure. And if I want to, I could just do a quick animation. I could go back to the image manager and do an animation, and you can kind of see that animation as the asteroid has movement here across these 60 images. So this is kind of just a fun little experiment. Again, you're just working with known objects here. If I wanted to, I could also do a stack. I could do a right click and view a stacked image. And if I want to, let me go ahead and put that on track motion. So what we're doing here is we're tracking that object, if you will. So we've stacked the images according to the motion of that object. So here we are. This is that object here. And you'll notice that the stars in the image are trails at this point. So it's almost like you had taken your mount and you had specified the motion of the object, but you've done it after the fact. So that's kind of a nice thing to be able to do. But again, at this point, we've only been working with known objects. Now we want to answer the question, what if I want to discover a new object? How would that look like? What would that look like? So what I can do there is I can go to Action, Synthetic Tracker. Okay, so I mentioned earlier, synthetic tracking is kind of this nice little technique for detection, especially as an amateur astronomer. So let's go to Synthetic Tracker, and it will prompt us for a sensitivity threshold. So how sensitive do you want the search to be? And 99% of the time, I just recommend using the balanced preset option here. So I click OK, and here's where we can specify what kind of limits we want on the search. So if I want to do a blind search, if I want to mostly just do search for all possible motions, I could uncheck those limits and just do that, and it would come back with 121,000 motion vectors for this particular data set. Now, if I want to, again, I could say, well, maybe I just want to look for main belt objects, main belt asteroids. And main belt asteroids would typically have a speed between around 0.2 and 0.7. So let's just take a look and see, just for the purpose of a very quick demonstration here, what that would look like. So, so this is 2,029 motion vectors. And again, what that really looks like, again, if you're familiar with stacking, you've got your 60 images, and you're going to stack them in some way. You can do a median combine, you can do an average combine. Ultimately, you're going to be, again, working with 60 images. Here, we're going to do that 2,029 times. So we're going to stack 60 images over 2,000 times. So I'm going to click OK. And let's just give it a moment here to do that. And also, while it's doing that stacking operation, it's also exploring those trial stacks to see if there are any detected objects. So it's already finished. And so that's the power of GPU acceleration. Again, I have this, I'm not going to go into super detail here, but you can configure your graphics device and set it up to do that. But here's the results. So we've come back now with our track navigator. These are all the detected objects in that field of view. And so what I can go ahead and start off with is I can say, well, let's compute the confidence in these detections. So it's going to tell us how confident it is that these are actually real objects. So I've got a column here to indicate that. So we have high confidence, and most of these are high confidence, but a few of them are low or no confidence. And then I'm also going to go ahead and load known objects with this. So it's going to tell me if these are also known objects. And of course, most of them will be, but this is a good result. So we've got our first result here. So we did a blind detection, again, on our asteroid over here that I was showing earlier. Again, that's 38826 is the number. And I can also just go through this list here, and I can just click through. If I want to, I could also double click on an object, and that's going to bring up a verify track module. And so what this looks like here is it's going to do an animation of the frames. And so it tells us if we want to, we can follow the object, or we could just let the object move and not follow it. So we have that way to animate the frames. Again, you can choose however many substacks you want to do. Now, once you have your object and you've decided you want to work with it, then you can do add observations. So if I click add observations here, then this is how you would generate measurements, astrometry measurements of the object.
Can I ask a question?
Oh, sure, absolutely.
So why are there other things sort of tracking the object in your image? Is that just, well, and what is that? You know, I mean, right, like there's a dot to the lower left of the
yes, right here.
Yeah,
That would be another asteroid
that happens to be moving
at
more
the same motion. A lot of main belt asteroids have the same motion.
Okay, thanks.
Yeah, so I'm not sure what, let's see if I double click on this one. So it happens to be the next result here. So it has a speed of 0.58 arc seconds per minute. The other one had 0.69. So the one's just a little bit faster than the other, but most importantly, they both have a similar direction. So 243 degrees versus 264 degrees. So the motion is quite similar for this particular data set. So if I want to, I can go ahead and create, measurements of each of these objects, but I'll just show an example here. So this is what that would look like. So I can click add observations, and what that's going to do, I can input the sort of the designation of the object. So it has a permanent ID, provisional ID, and so forth. There's a lot more detail on what these mean if you get interested in pursuing this further. But suffice to say, permanent ID is its number, and then provisional ID, whenever an object is newly discovered, it has a provisional ID. So that's typically the year followed by some alphanumeric collection. So I click OK here, and now we've got 3 measurements of that object. So if I click on the first measurement here, I can zoom in a bit, and you can see that's the first substack of the object, and I can click on another measurement here, and then finally the last one. So you can see what we've done here is we've generated measurements of that detected object. And so if I wanted to, I could generate a report. We can do there's 2 different types of reports. The original format was MPC 1992, came out in 1992. And then the more recent one is called ADES. It's an acronym, but this one is still popular. So again, I could spend a lot of the discussion just talking about all these little nuances here, but suffice to say, what I'm getting at is you basically image the object, you're able to detect it, and then you're able to generate measurements of it. And so that's what I'm showing here. And then, of course, you could send that report.
How come you don't have 60 measurements of it?
Right, yeah. So if you wanted to, you could do 60 measurements, but the Minor Planet Center prefers that you only send 3 observations per night, typically 3 or 4 per night. And the way that works here is that you want to certainly, when you're focused on these fainter objects, you want to generate your measurement on a substack of the object. So let's just take a look at that in more detail. So here's this object. I can go to the track position window. And if I just go ahead and look at it on individual exposures, you can see that this particular object, it's fairly bright. I can see it on individual frames. But if I take a look at a fainter object, let's take a look at this one here. So this is 2018 RW19. This one is barely detectable even with substacks. So what we've done here is again, this is an animation of 3 substacks, and it's very faint. If we were to look at that with our single images here, you can see that it just kind of gets lost in the noise on these single exposures. And so you wouldn't really want to generate measurements of it on all 60 images here, there would be too much noise and the measurements wouldn't be very good. They would have too much error in those measurements. And so that's one explanation for why, but the other is that, again, Minor Planet Center, the organization that takes in these measurements, typically they don't want more than 3 or 4 measurements of an object per night. And so if you've got your 2 hours of image data, what you would probably want to do is, again, just divide that up into 3 or 4, again, subsets, and then you can have the arc length would be the same, but you've now reduced it down to just 3 or 4 measurements. Any other questions at this point? Okay, so what we've done here again is, we've taken, this is just one example. This is using the synthetic tracker, and it came back with these results. So it's pretty cool that, again, this is just using, amateur astronomer equipment. You can do these kind of measurements. You can do this kind of detection as well, and that's in my mind, that's pretty fascinating, especially that you could actually make a potential discovery with this. Now, again, that's one part of the presentation here is discovery, but also asteroids are interesting in that you can also do photometry with them as well. And so here I will focus on another data set. So I'm going to clear out this workspace here, and I'm going to show you another example here. This is Asteroid 1884 Skip. And so what I've got here, these are, let's give it a moment here, the 240 images. Total exposure time is 4 hours. So each exposure is 60 seconds or 1 minute in duration. And what I did here was I wanted to measure its rotation period. So we've got an asteroid and we want to answer the question, how fast does this asteroid rotate? So again, 240 images here, and I'm going to go ahead and change my observatory setting here because I took these images from a different location. So this is H06, that is Mayhill in New Mexico. And so let's go ahead and view images here. So this is an observatory, again, from the itelescope.net network. So I'll give it a moment here to finish loading up these images. And here we are. So I've got, this is what that looks like here. So again, I could animate the frames. And if I zoom in a bit, you might be able to see the moving object. It's pretty bright in this case. So we've got our asteroid here, and it's just moving along the field of view. And what we would like to do is we would like to take measurements of it. In this case, 1 measurement per image. So here, this kind of is actually the opposite. Where previously I mentioned you only want 3 or 4 measurements per night. Well, in this case, if you're doing a light curve, you actually do want to have basically 1 measurement per image. And so light curves are different. In this case, you're not trying to come up with an orbit of an object. You're trying to measure its brightness over time. So a couple ways to do this. This is a known object. So if I wanted to, I could go to File, Load Known Object. And so let's just give it a moment here to finish that. And so here it is. It's the first result. This is Asteroid 1884 Skip, and it shows us the trajectory of that object. And so again, if I were to do the animation, you could see how it moves across that line there. But basically, again, what we want to do is try to create that light curve. So what this means is we're going to be invoking the photometry module, and lots of ways to do this, but I like to start off with just finding comparison stars. So I'm going into a bit of detail here for those of you who might not be familiar with photometry. I realize that this is a bit of detail to take in, but I promise I'll make it a little bit quick here. So find comp stars. This is basically differential photometry. So you're trying to measure the brightness of the object in a precise fashion. So comp star finder kind of tells us what would be good comp stars to use in this particular field of view. So I'm just going to go ahead and choose a few here that are on this, again, this plot. And so let's just go ahead and I'll add up 5 or 6 comp stars here. And once I've done that,
make sure they're not variable or something like that.
Yes, that's exactly right. So we want to make sure that these are not variable stars. And so what I do with that is I take an initial collection of comp stars. And what I'm going to do is generate data. So it's actually going to measure all of these comp stars across the field of view here and across the image sequence. And so we can look at the graph here and we can see what that looks like. This one doesn't look so good, so I'll just go ahead and remove that one. But these other ones we can probably work with. Now, if I want to, I can also verify my star catalog settings. So I'm using the Atlas catalog. And this is a very good catalog to use for photometry purposes. And so I'm just going to go ahead and click OK here. And again, this is just a starting point, but I can go ahead and, if I want to create my light curve, let me go ahead and go to the first position of the object here. So again, known objects, I can double click on it and I could say create marker 1. So I'm indicating the first position of the object. And then I can scroll down a ways and then go to create marker 2. So what I'm really doing is I'm defining the motion of this object. And now I can say create photometry from markers. So let's just go ahead and give it a moment to see what it comes back with here. So we've now generated 240 measurements, one for each image and the data set. And I'm just going to go ahead and plot all sets here. And so this is kind of what that looks like. So it's basically generated a light curve. And again, I can go ahead and give this a title. The correct title here would be Skip 1884. And so we've got kind of, this is what you consider to be the raw plot of the measurements. And so if I want to do so, I can go ahead and do an initial period search. But before I do that, it's always a good idea to, well, let's just go ahead and take a look. I'll show you what that means later, but find period, I can give it a start and stop range. So what we're saying here is we want to search all periods from between 0.5 hours and 12 hours. So we're going to give it a lower and upper bound on that search space. So I click find period, and now it's come back with a 2.89, 2 hours is its first analysis here. So that's actually a very good result. If I go to the tools menu and go to light curve database, I can actually consult a database of known objects here. So if I click on search and 1884 Skip is one of these results, it says 2.8887 would be a rotation period. And so this is actually pretty good because keep in mind, again, this is only one night of data. So as before, it's, even with light curves, it's a good idea to have more than just one night of data. But this is just to show you what is possible, and what you can do. So again, I've talked a little bit now about detection of asteroids, discovery of asteroids, and now here I'm talking a little bit about measuring them. And in this case, you can measure their brightness over time, and using that information, you can get an idea as to its rotation period. And so this is all pretty cool because again, you can do this with amateur class equipment. So I'd like to take just a moment here if anyone has any questions. Okay, so moving along here, again, if I wanted to, I could clean this up a bit. I could certainly take a data point here and I could, delete that. So this is your typical interface here. You can work with the raw data. You can also apply object data. What that means here is that if you search for the object, it's going to give you additional information on it. So the phase angle and so forth. What that allows you to do is you can also compensate for light time correction. You can apply H minus G correction. And so this becomes more important whenever you have several nights of data, because with multiple nights of data, you start to have these offsets, and it's good to be able to have those corrections applied. But again, we'll still have a very similar result as we did before. Okay, so that covers this particular data set here. And again, this is asteroids.
Can I ask, do you need to worry about like atmospheric refraction, air mass, that kind of thing?
Yes, you can. Whenever you export the data, it's able to compute what air mass. Yes. So if I go to File, just to give you an example here in the photometry sets, that's something that's typically exported as a value. Let's see here. So export
is, would that affect the period, like of your the calculation of the period of the rotation, if it's going through, or I guess if you track it over a period of several hours, right? So it's going to be falling or rising in altitude, so there'll be a little bit of bending. Is that right, or am I imagining?
Sure. Well, what you're focused on is you want to make sure that, okay, these all have some what we call amplitude amount. So this is the amount the amount of magnitude change that you can see here. So this one here, you might see 0.3 magnitude, 0.27. So it's going to vary in brightness by this, a quarter magnitude, let's say. So what you would want to make sure of is that again, this is just like any kind of measurement, it's going to have some error bars in it. So you want to try to make sure that your error bars are going to be significantly lower than that amplitude. So if you're going through a lot more sky, or you have more air mass, then as long as you still have good signal to noise ratio on that object, such that you have the error bars are lower than that amplitude, then you should be okay.
Thanks. Yeah.
Okay. Okay. Any other questions? Okay, moving right along, I'm going to go ahead and close out this data set, and then let's take a look at the James Webb Space Telescope. So this is kind of a fun one. It's just a once in a lifetime opportunity to have imaged it as it was en route to the L2 point. And so here I've got 179 images, and this spans a total elapsed time of 4.2 hours. Anyway, here each exposure is 1 minute in duration. And what I'm going to do is let's just go ahead and take a look at the images here, the image data. So as before, I'm going to load these up into the image viewer. So I'll give it a moment to do that. And if I want to, I can zoom out a bit. I can animate the frames. Now, you may or may not see it, but here it is. It's kind of trucking along through this field of view. You can see that moving object here. Now, another way to do this is I could also attach ephemeris information to this data set. And this is actually somewhat of a new feature. So with this interface to JPL Horizons. I've just recently added it. So we have a JPL Horizons interface. And what you can do here is you can actually use this tool with a wide variety of objects. They don't have to be asteroids. They could be spacecraft. They could be, some other object with a two-line element. So for example, if I do a major body lookup, this is actually going to bring up a list of results here. And they've got 482 what they consider to be major bodies, as opposed to small bodies. So a small body would be an asteroid or a comet, but a major body, to use their terminology, would be a planet, it would be a spacecraft. So for example, if I type in J, James Webb Space Telescope is one of these returned objects. And so it has an identifier. Every object here has an identifier, and it just so happens to be -170. So I can apply that target ID in this interface form here. So what we're basically saying is that we would like to generate ephemeris information for this particular target. And we'd like to do so and attach it to this data set of images. So what that means is I'm going to request all of this information of that object pertaining to when these images were taken. So I'm going to choose ephemeris attached to data set. And so it's going out to the JPL Horizons portal, and we've just now, it's already returned with the result here. So all of these columns have been populated for each image. One of these is the object in the field of view? So that's kind of a basic question. You'd like to know, did you actually capture the object in the field of view? So either yes or no. And it also tells you the speed of the object, the position angle of the object, the altitude of the object above the horizon, azimuth, and so forth. So you get all this useful information. And what you can do is once you've applied that ephemeris information, now I can actually just click on an image in the image viewer manager, and you'll notice that it tracks it in the image viewer. So I can actually just go ahead and scroll through here, and you can kind of get an idea of what that looks like. So we're able to track the James Webb Space Telescope across our 179 images. And you can probably see already, it does have quite a changing brightness. Another way I can do this is in false color mode. So I can toggle that, and you can notice that, again, it gets darker and then it gets brighter. So it certainly has a change in brightness over time. Another way to do this is I can also select all of the images here and do a max combine. And now you can kind of see that better. So it started here, this was the first image. And so it was a little bit faint. And then it progressed to be, eventually got brighter, pretty bright here, it got a little bit fainter. Now it got really bright. So now what we'd like to do is actually analyze this with some numbers. We'd actually like to measure it, have some meaningful measurements taken of this object. So what I'm going to do, like I did before, is I'm going to invoke the photometry module. So again, we can start off to find comparison stars. And so I'm just going to go ahead, as before, add comparison stars to my list here. And then I'll probably get about, again, 5 or 6 of these comp stars. Okay, so I did 7, and I can always remove 1 or 2 that don't look very good. So let's just give it a moment here to finish up. And probably want to get rid of this one, and maybe this one too. So I'm just going to start with that. That's just the first stab at it. But again, the other nice useful feature here, because I have attached ephemeris information, before I had this feature, I tried to do a photometry set with this object. So I would try to say, well, here it is. I'd create marker 1, and then I'd go over here, for example, create marker 2. You'll notice that the object, unlike in the previous example, it does not follow exactly a straight line. So you can't really just say create photometry set using markers for this kind of object. So if I do my, it's almost a straight line, but it kind of deviates a little bit from that. So this little bit of deviation here is just barely enough that you wouldn't get super good results with this approach. So that's why now, if I want to, I'm going to do photometry set. I'm going to create photometry using ephemeris information. Now, the other way I did it before I had that feature is I would just divide up the data set into sets of 20 images each, and then I'd have a marker 1 and 2 for each subset. But this is a lot easier when you have ephemeris information. So I'm just going to go ahead and try that out. So here we are. I'm going to get rid of that old data set. I don't need that anymore. So here we've got one photometry set, 179 measurements. So one measurement per image. I'm going to go to plot all sets here. And here we are. This is the light curve of our James Webb Space Telescope. So again, that's the raw plot. And if I wanted to, I could click on a data point here. Okay, so that moves to that particular image, and you can see how it's that kind of that intensity there. And if I go to one where it's a bit fainter, then you'll notice it is indeed a fainter object there, presentation. So this is in fact the light curve in University of Hertfordshire. I forget the exact. Anyhow, in London, they had a light curve. It looked very similar to this. So if you're interested, you can pursue that as well. But yeah, so it's pretty cool. Again, amateur equipment, you can take these kind of measurements. You don't need a 1 meter class telescope. So are there any questions?
So I assume the reason for the odd light curve is just light reflecting off different surfaces of the telescope. Is, you know, like it's really close, and the same thing, by the way, for the curve versus straight line. It's so close to us that we're really seeing details of its, you know, curved orbit as opposed to, you know, something so far away. You know, the curve is sort of a straight line.
Correct. Yeah, this would be exactly correct. Glinting off of surfaces of the spacecraft. So, and especially this kind of magnitude change. This is basically 3, you know, magnitude. So it went from magnitude 13. 0.3 to magnitude 16.7. So it's, yeah, absolutely correct.
Yeah, I have a question. I would suspect that the center of brightness of the telescope is not at the center of mass for a large part of this light curve. Are you able to detect a kind of oscillation due to that?
Oh, are you saying can we determine its other properties of it, like it's kind of its you know, like with the asteroid?
The center of mass is going to be basically around wherever the primary mirrors are and the equipment is. It has this big boom out here with a big sun sail that's sticking out there. That's very low mass in comparison. This will be rotating around. Would you be able to, at this remove, be able to detect a side-to-side oscillation rather than the straight line that the center of mass would tend to make in the sky. Are you able to get that sensitive?
Right. Possibly. I don't know the answer to that just yet.
Oh, okay. Be something interesting.
Mhm.
Thank you.
Sure. Any other questions? Let me ask a question. Have any of you worked with asteroids before, or what kind of experience level? Have any of you tried to image, on purpose, take images of asteroids?
I tried a couple of times. There were some near-Earth asteroids that were known to be doing close passes, and I imaged them. I think it was, I should look at my astrobin for the names. One of them was Florence, and I don't remember the second one. But most of all, and the way I work with asteroids is by, somebody mentioned at the beginning, by removing them from, by checking that pixel inside removes them correctly. I had 6 of them in the same, in various subs of the same image once.
Yeah, you were probably somewhat near the ecliptic, I suppose.
Yeah.
Mhm.
Yeah, I've done the same as Francesco, just on these more famous, near Earth objects, just try to catch them, but never done any analysis, just because I don't know anything about it. I just know the word photometry and that's it. I did have one image of Andromeda Galaxy that I was blinking through and saw something moving there, and it turned out to be an asteroid. But again, didn't know what else to do, but try to figure out what it was, and then just kind of reject them in the stack.
Sure. Now, when you have tried to image, were you configuring your mount with tracking to track the asteroid, or to do that after the fact?
I'm trying to remember. It's been a while. I may have used APCC, which is the kind of new fancy control program for the astrophysics mounts, and it has a Horizons interface also.
Okay.
And so you can program it to try to track, but it's been long enough now that I don't remember if I ever got that going. I think I did, though.
Okay. Yeah, there is also a session planner module I've just recently added as well, which basically what you can do here is type in a start and stop date. So you can click some of these helper buttons, but basically you give it some time interval as well as a step size. And this is a way to generate some ephemeris information. So you could do this again from JPL Horizons. And so if I want to, I could pull up Asteroid Skip and attach it to the session planner. And here we go. It now populates with this list. And we can know the coordinates of that object at these given dates and times. So it's a helper tool. It's kind of nice to have this capability. And again, you could use that not just for asteroids or comets, but again, I just showed the James Webb Space Telescope. So you could generate ephemeris information on these other objects as well. Now you might be wondering, what is Find Orb? Find Orb is a really useful tool. And what I like about it is that you can use Find Orb on really just newly discovered objects. So for example, if I go to the tools menu, I'll just give you an example here, but so if I had some observations of an object, I showed earlier 38826, what I can do here is let's suppose that we just had these recent measurements of this object. Well, I could click view and find orb, and what this does is it pulls up this orbit solution here, and it also tells you the quality of those measurements. So these two columns here, these are the error and right ascension and declination, and so these are in arc seconds, and so you typically want those to be below 1. So typically 0.5 and below is good. But anyway, what you can do here, as I'm trying to point out, is you could then attach that solution, that orbit, into the session planner. And so I can tell it to use that find orb instance. So basically Tycho is going out and searching for find orb instances, and I can click OK. And again, it's going to, well, okay. So as it turns out, 38826 is not visible. I had a filter. If I refresh it, then you can see. So this would be the result. So the altitude of the object it's below the horizon for this particular object. So that's the altitude column there. But lots of ways to generate. If you wanted to have a session plan, if you wanted to image a particular object in the future, that's one helpful tool for that. So any other questions or comments or thoughts?
So related to what we were talking about before the talk, I take it that there is no way for you to figure out, not ask somebody else for the orbit, but to take a guess at, the full orbit of this object based on, I mean, you probably can't do that, as we said, from one night's observations anyway, but
well,
what can be done in that regard?
Yeah, let's go. I can just give a quick example here. So let's go back to that data set Tycho user guide. And what I'll do here is I'll just pull up, again, this is an example of one night of data. So I'll go ahead and change my observatory back to Sighting Spring, Australia. Let's do that real quick. And so if I pull up, this view here, and I can go back to my normal presentation. Yeah, what I can do is, again, let's run this hypothesis or this thought experiment where let's suppose it's a newly discovered object. So I've run through synthetic tracker and it came back with some results. So here's the track results here. And again, maybe had high confidence on this object. Okay, so if I double click, you can see this is a real object here. It's very faint, but nevertheless, it is presentable on these three substacks. So I'm going to go ahead and add those observations, and I can just give it a tracklet identifier. And so what we're doing is we're going to pretend that this is some new discovery. So what I can do here, again, these are my three measurements. I can right click them and then choose view. And then I can say view and find orb. So this is going to bring up find orb, and it's going to compute an orbit solution. So it's going to try to take those three measurements, and it has some, fitting here, and it's going to give you some, residuals. These are, again, those two columns. So you do have an orbit that's been computed, but it will have high uncertainty. So it's probably a good enough orbit that you could follow it up the next night. You could maybe even use it to follow it up the night after that. But could you use this orbit to predict where the object is going to be 2 months from now? No, you couldn't. It just has too much uncertainty. So, a single night of observations, that's usually good enough to get you where you can follow it up the next night, especially if it's a main belt asteroid. So if it's a slow moving asteroid, no problem there. But yeah, it's when you try to use this initial night of observations to try to predict where it's going to be several months from now, that's where you run into issues. And that's where you need to have more data.
So, so like if we wanted to know the mass of the asteroid,
Mhm.
because you mentioned that somewhere early in the talk, right? Somebody found an asteroid that was such a size, presumably if it's rock, its mass. So how can that be done? I mean, like, what would you need to do that?
Right. So I was talking about the diameter, size, and what that usually amounts to is you do the absolute magnitude of the object. That is and it's albedo, so it's reflectivity. So you're considering not just the orbit of the object, but also its brightness. And if you know its brightness as well as its albedo, you can kind of get some ideas to how large it might be. So that's kind of how they do that. There's an online calculator if you wanted to play with it, where you can type in the absolute magnitude of the object, as well as I believe it's the slope of it. So 0.15 is the typical default value, and then it will give you some diameter estimation. So it is just an estimation, but it's perhaps considered a starting point.
All right. I guess I was confused. So the orbit itself doesn't tell you anything about the mass, right? It's just the distance it is from the sun tells you about the orbit.
Correct.
Yeah. Okay. Okay. Thanks.
Yeah.
Any other questions or comments or any other stuff for Daniel? All right. Well.
Yeah, I actually
Go
had
ahead.
a question and such. Yeah, I kind of got here late and whatnot because it took me a little longer to get on. But is this like a tool that you have just hosted on your computer, or is there like a GitHub link that people could check out? Such that was my question.
Sure. Yeah, this is a tool. It's available online. Tycho-Tracker.com is the website. So, or if you just do a Google search on Tycho Tracker, it should come up there as well. So it's, I go to the About page here. Yeah, so that would be the link. So here's the web page. And I talked a little bit earlier about some data sets. So if you go to the download menu here, there are some data sets available on this web page. So the one I was showing earlier was the DS3. That's your 60 images. It's about 100 megabytes in size. And so if you wanted to download the tool, you could also download some data sets to play with. IVAR light curve, this is one that if you're interested in photometry, then you could download these data sets. There are 3 nights of observations here, or measurements, and you could create your own light curve from that. Yeah, so that's the website, tycho-tracker.com.
So to be clear, it's a program that's downloadable for free, I guess, but not open source. Is that correct?
Yeah, it does cost money. So it is, there's a trial version, so you can try it for free for 30 days. Yeah.
Thanks.
Yeah.
All right, any other questions or comments? All right, well, I guess not. So please unmute and applaud. That was a great talk, Daniel. Thank you so much for.
Thank you, Daniel. Very clear.
Thank you.
Thank you, Daniel.
Thanks.
Thank you.
Thanks.
Appreciate it. And if you do have any other questions, here is also my email here. So, okay.
All right, we really appreciate it. And I guess that's the end of the March Imaging SIG meeting for SJAA. And thanks everybody for attending. All right.
Yeah, that was a good demo of the tool and stuff. Thanks. Looking forward to more.
Appreciate it.
Bye.
Bye.
Bye, everyone.
Thank you. Bye.
Bye. Thank you.